Okay. Okay. Just start. Okay.
Welcome to the session, keynote session on accelerator applications. So we have a lot of different papers in this particular session. So the first paper is presented by Zihan. He's currently a PhD student at Shanghai, in Shanghai Tong University in computing science. He's supervised by Professor Jingwen Leng, and his research interests are in computer architecture, AI systems, and optimization.
Okay. Hi, colleagues. I'm Liu Zihan from Shanghai Jiao University. And today I'd like to introduce our work to accelerate nearest neighbor search in arbitrary dimensional spaces with ray tracing hardware, aka RT-Core. And surprisingly, ray tracing's ability is far beyond high-end video games. And today I will go through the typical nearest neighbor search and ray tracing pipeline. Then I will introduce our solutions in detail. Nearest neighbor search aims to find several nearest points among a dataset given a query. In industrial practice, we often relax the search accuracy requirement for higher search speed, which we'll call it approximate nearest neighbor, aka ANN search. Notice that ANN search may give false positive and false negative. The quality of ANN search can be evaluated with recall. And ANN search is widely used in various machine learning applications like LLMs, point cloud, and so on. And typically, researchers will utilize FIRES from Meta and SCANN from Google to accelerate. ANN search consists of two major techniques, indexing and encoding. The former aims to reduce the search points needs to check, while the latter aims to reduce the storage overhead. Together, they speed up the search process. And among various techniques, inverted file index with product quantization, aka IVF-PQ, is the most popular and best performed. The IVF index will organize the search points into several clusters and only check the points from nearest cluster when searching, while the PQ split the points into several subspaces and cluster in these spaces, and use cluster centroid's ID to encode the original projection. When searching, we first need to calculate the distance lookup table between query projections and cluster centroids. Then we look up the table with encoded IDs to accumulate the overall distance. In this work, we mainly optimize the PQ process, which means all algorithms utilize PQ can benefit from us. We identify that in PQ process for a given query, not all cluster centroids are actually used by its true top 100 nearest neighbor. As shown by the heat map and the bottom left figure, for SIFT dataset, only a quarter of the centroids are used. This gives us an opportunity to get rid of useless calculation and looking up. While notice that though used centroid seems randomly distributed in memory spaces, they are closely distributed in metric space. After we sorting the centroids by their distance between query, they collocate closely in the left part of second heat map. And statistically, by selecting top 40% nearest centroids, we can cover over 90% of actually used centroid. However, conventionally, to get the nearby centroid, we still need to calculate all pairwise distance, while the ray tracing relieves us from doing that. Originally, ray tracing aimed to render realistic photo-like pictures by simulating the physical behavior of lights. It involved intersection check between millions of rays and trillions of triangles. And to accelerate, researchers organized the triangles into bounding boxes and the boxes into trees. The intuition is that when a ray misses a child of the tree, all objects bounded by the child tree can be ignored. This significantly reduced the complexity from ON to O log N. We can use the NVIDIA Optics Toolkit to program the RT-Core. We first place hittable objects in a space. Then we set the viewpoint as the ray origin. Once these are all set, we can launch the ray. Finally, the article will return the hit results and invoke corresponding shader program, like miss, close hit, any hit. And fortunately, we can use this technique to avoid large amounts of useless pairwise distance calculation, since intersection indicates being close. And intuitively, we can replace the concept of ray tracing with concept of ANN search. To be specific, we replace the hitable objects with cluster centroids and rays with cories, and we get a simple mapping from ANN search to ray tracing hardware. As shown in the right figure, we place hitable spheres at coordinate of cluster centroid and shoot rays from coordinate of cory. A hit indicates a centroid is close to the cory. We then calculate the actual distance for later distance lookup and accumulation. For other missed centroid, we ignore them once and for all. However, there are several obstacles between our intuition and actual solutions. I will introduce them one by one. And the first question is that how large should we set the hitable spheres? We could miss potential neighbor if too small, while compute too much redundant distance if too large. And we observe that the region density impacts the radius setting significantly. As shown in the bottom left figure, centroids in high density region only need a very small radius to cover all potential neighbors, while centroids in low density may even cover less than 100 points with the same radius. So we set the sphere radius depending on the density of region of centroid located. Moreover, there is also power law in radius. By applying half of the radius, we still get 90% of the true neighbors. And this gave us an opportunity to trade off between quality and speed. The second question after determining proper radius is how to apply them with efficiency. Directly changing the size of hitable spheres will trigger scene reconstruction, which costs a lot. While the ray tracing provides a concept of ray travel time, see the following example. Originally, the travel time is set to be 1, which means the ray will travel at most 1 unit of time, and the ray will hit all area of the sphere. While with half of the travel time, the ray will no longer hit the sphere from the same distance to the sphere center. Only when the ray is getting close to the center, it can hit the sphere again. Thus, we can control the hitting area. In another word, radius with efficiency. Notice that now all radius are set to be identical constant. The concept of time have another clever utilization. Originally, when we calculate the actual hitting distance, we need to query the coordinate of sphere from the global memory, which costs a lot. While with the hit time, we can get the actual hitting distance with very simple math. Since currently all radius are identical constant and hit time is stored in the register. More aggressively, we can even save all the math calculation. As the bottom left figure shown, there is a strong positive correlation between total distance and hit count, which is a count of in how many subspace the cory projection is close to the centroid's projection. So we can simply count the hit in all subspaces and sort them, which is an effective approximation of actual distance. Moreover, we can add more spheres for finer grain counting for higher quality, as shown by the blue part of the figure. The above contents are all about L2 distance, and we also support inner product. Notice this is the distance calculated by the L2 distance calculated by the hit time. And the inner product can also be represented with the L2 distance. While the XQ squares and YQ squared part are fixed when the cory is fixed. Well, notice that there are unknowing XE square and YE square force us to query the coordinate of centroid. However, since XE square and YE squares are constant, we can adjust the radius of sphere to be square root of original radius square plus XE square and YE square. Once we replace the radius with the new one, we find XE square and YE square are eliminated. And all we need to do is to fix the radius at offline and then no online overhead is introduced. Notice that conventionally researchers need extra dimension to eliminate this annoying part, but we do not. Finally, there is small point. Notice that RT-core is only responsible for finding intersection, while the shader program actually invoked after hit or miss is executed with CUDA core. So if we accumulate the distance on CUDA core, we cannot pipeline them. So we map the distance accumulation to the tensor core for fully pipelining. And we pad the B matrix to force the cubulas to use tensor core. And our padding shape setting is as following. Now we've introduced our solution. Here comes the evaluation. We evaluate our work on 3 datasets with 1 million and 100 million points, where SIFT and DEEP are L2 metric and TTI is inner product metric. The baseline is FIRE's GPU. We evaluate our work on Ampere and ADA GPUs both. We mainly evaluate our work with recall and throughput, both higher the better. The baseline algorithm is typical IVFPQ. For some baseline, we add graph index for fairness, which makes the baseline even more stronger. We have 3 settings from lower quality to higher quality, from aggressive counter-based accumulation to exact distance calculation. Overall, we get at most 8.5 times improvement in search throughput at lower search quality and 2 to 3 times improvement at higher search quality. And our aggressive counter-based approximation and pipelining is also effective. With all of this optimization enabled, we got more than 4 times improvement at lower search quality and 2 times improvement in higher search quality. We also verified the effectiveness of our algorithm only on a Tesla A100, which is a GPU without RT cores. Our algorithm still gets significant improvement at lower search quality. While in higher quality, there are little redundancy can be utilized, so there's no improvement without the efficient distance calculation of RT cores. While on the other hand, we verified the impact of performance of RT cores, and JUNO behave better on Gen 3 RT cores on ADA GPUs, and turn out that the stronger the RT cores, the better the JUNO is. Here comes the conclusion. In JUNO, we identified the efficiency of typical ANN pipeline and leverage the RT cores to avoid these redundancy. With several clever optimizations, we get significant improvement against the baseline. And my presentation is over. Thanks. And all question discussion are welcomed. Okay.
When you map these to the RT4, from a programming model perspective, do you face any different challenges? Do you like the RT4? Like, do you like a different programming model? Like, how easy or how?
Oh yeah, the major challenge we face is that the RT core or the programming API is closed. We cannot manipulate the GPU with CUDA, PTX, or some flexible ISA. We only can use the RT core with the provided APIs. So here's the question: the RT core can accelerate the tree traversal, but the condition on the tree nodes are fixed. So if the RT core can provide some more programmability, we can adjust the comparison. We can adjust the condition on the tree node, and we may get even more potential. Yeah. Okay. Thanks.
The next speaker is Yuhao. He's a second-year PhD student at HK University and Guangzhou, and his research is displayed in field architecture and high-performance computing. He's currently a visiting student at the University of Rochester.
Thank you, Professor. Okay, thank you for attending my talk. I'm Tianhao Ge, and today I introduce our paper, NGAP long-blocking large-scale automated processing on GPU. This work was jointly performed with our collaborator Tong and my advisor Hongyuan Liu. Finally, the automata are commonly used for pattern recognition, and the automated processing engine usually takes the rule set and the input streams as 2 inputs. And the rule set defines the tautology of the automata, which will be then used to match multiple input streams and generate the matched result. And the automated processing plays a crucial role in a variety of applications, including the data analytics, machine learning, bioinformatics, and network intrusion detection. So with the advent of the big data, the number and the size of the automata are expanding. For an example, for the network intrusion detection system, it has seen a 90% increase for the rule set from 2017 to 2023, which each rule represents one automata. So achieving higher throughput in processing large-scale automata is our primary goal. So today I'll talk about some challenges when we are trying to deploy the large-scale automata on GPU and how we address them while the long-blocking automata processing. Automata processing operates in an iterative manner similar to some graph algorithms. In each iteration, it tries to match the input symbols in the input streams with the active state, and then move to the neighbors to continue processing for the next symbol. And when we encounter a reporting state, it indicates that we found the expected pattern in the input streams. And the always active state, which are represented in the hexagon, they are always considered active in every iteration. So this process can offer several levels of parallelisms, including the input streams level parallelisms, the automaton, and the state. So it is very suitable to be deployed on GPU to achieve higher performance. Previous work typically use a data-driven approach to enhance the GPU utilization. They first assign the state to the thread and then do the extending and matching. The matched states will be stored in another worklist, which will be used in the next iterations. So the prior works will use a double buffer worklist to distribute and balance the work. However, we have observed that the parallelisms is still insufficient during the execution because one iterations can only process one symbols at a time, which delays the executions of subsequent symbol. And these limitations can also lead to some other problems. So the first problem is the thread underutilization. Although the state in the worklist run in parallel, the length of the worklist in one iteration depends on the number of matched states, which may not be enough to utilize all the threads. And we observe that the average thread utilization for 20 applications is only 32% in blocking automata processing. And some applications are less than 3%. It means that the GPU resources are still underutilized. And the second problem is the redundant computation. In each iteration, the always active state will be added to the worklist, and all generated state from this state can be mismatched after several iterations, and we refer these symbols as the pattern. We notice that typically the size of the pattern would not be very long, and the prefix of the pattern can repeat multiple times. It implies that the computations may become redundant when we are matching these repeated prefix streams. And our observation is that this prefix significantly contribute to the overall computation. For example, if we can skip over a prefix of length 1, we can avoid computing about 61% of the string. And these ratios can increase to 93% when we skip over 5. So there are a lot of redundant work during the processing. And the third problem is the poor data locality. Since the state in the worklist are distributed evenly and randomly among the thread, state generated from one thread can be assigned to another thread in the next iteration. And this can lead to a loss of the data locality. And we also observed that the L1 cache hit rate is only 23% for blocking automated processing. So we found these challenges, they all share a same problem. The computation can now be scheduled over different iterations. So our key idea is to allow thread working on different symbols simultaneously. If the state in the work list knows the symbols need to match, it doesn't need to wait for other state to proceed. Then the synchronization between the symbols doesn't exist and making the whole process non-blocking. The non-blocking processing can leverage the parallelisms across different symbols in the input streams, and it will making the matching process more efficient. So we propose the NGAP to implement this non-blocking automated processing. And we use a single work list for all iteration instead of a double bubble work list. And we represent each element in the work list as a pal that contains the symbol index and the state and the symbol index. So each thread can be aware of the symbol and the state it needs to match. And a sliding windows is used to fetch the pals from the work list. And so it can make sure that each thread has the balanced work. So based on the NGAP, we propose 3 optimizations to address these problems. First, since the NGAP can handle state for multiple symbols, we prefetch the match between the always active state and multiple symbols to the work list in a batch. And these commutations were initially planned to be processed in later iteration. So therefore, prefetching can significantly improve the thread utilizations, especially when there may not enough state to be processed at the beginning. And then we use the prefix memorizations to reduce the redundant work. We pre-compute the result between the always active state and all possible prefix and store them in the memory. So by doing so, the commutation can be skipped while the table lookup. And the third optimization is the work privatization. We use the work privatizations to improve the data locality. In the work privatization, each thread can decide whether it should continue to process the extended neighbor rather than directly write them back to the shared work list. And we also have a divergence aware policy to avoid the warp divergence. When most threads in a warp have no state extended due to the mismatch, it will cause the warp divergence. So we will calculate the active thread ratios on the fly. And if most threads are idle, we will disable privatization. Finally, we put it all together. Although we propose 3 optimizations to address different challenges, they share the common requirement. The work list must be able to handle state from multiple symbols. And we also allow NGAP to use different parameters for different optimization so they can be tuned for better performance. And in the evaluation, we compare the NGAP with 3 GPU baseline and 1 CPU baseline. And we select 20 applications from 3 different benchmark suites. The code is compiled with the CUDA Toolkit 12, and we run them on a machine with NVIDIA RTX 3090. For the overall performance, NGAP significantly outperform other designs. Compared to the GPU baseline, NGAP can achieve about 7.9 times speed up and up to 900 times speed up across 20 applications. And for the CPU baseline hyperscan, which we don't put it in this figure, NGAP can achieve about 11 times speed up. And we also provide a performance breakdown to illustrate the impact of our 3 optimization. While the NGAP may slightly, the basic structure of the NGAP may slightly decrease the performance by about 10%. our three optimizations can improve the overall throughput on top of the NJAP. And in conclusion, we present the long blocking automated processing with three optimizations to address three identified challenges. And our work is also available on GitHub. Thank you for your attention and feel free to ask questions.
Looks like you have to store the edit state sets for not just one symbol but multiple symbols. So we need to increase the memory utilization. For example,
right.
If you have 56 symbols, if you memorize a pair of symbols, you have to increase the table size from 256 times 256.
Right. So the prefix memorization will cause more memory space to store these tables. And in our paper, we'll also provide calculations about the overhead on the memory and overhead on the pre-processing. And we also propose some small optimizations to make the space for the memory smaller. And I doesn't put this part in the slide, but you can check these details in my paper. Thank you.
Investigate why achieve the like I think the reduction in the
you mean your question is where is the performance beta comes from? So there is a breakdown of our performance speed up, and you may notice that although the basic structure of NJP have some performance slowdown from 1 to 90%, this is because we have to maintain the more data structures. For example, the pairs of the state and symbols, and this will cost more times to process these data structures. But based on the NJP we post three optimizations, you can see the most significant speed up is the second optimization, which is the prefix memorization. So in these optimizations, we remove some redundant commutation. So the number of commutation becomes smaller, so it can get some speed up.
So you mean the
yeah, for the roofline analysis, in fact, in our paper, we have subsections to analyze the roofline. And in fact, you can see in this, we have a figure in our paper, and this figure shows that our NJP is latency bound. And for other GPU baseline, it can be a compute bound. So you can check our paper for more details. Thank you.
I wanted to ask, what's the motivation behind doing this on a non-deterministic automaton? Why cannot you just determinize it, and then you don't have this issue of being in multiple states at the same time? Is it infeasible for some reason, or?
I'm sorry. You mean your question is about the motivation? Why can making the process non-blocking or
why cannot you take the input automaton and make it deterministic so that you don't have this issue of being in multiple states at the same time? That's my question.
Because in the GPU programming, you have to synchronize between every iterations. But in our design, we try to remove them or try to make the scope of the synchronization more smaller. And the synchronization can bring some overhead to the processing, so we can get some speed up from this point.
But the synchronization only happens if you're in multiple states at the same time. If you have a deterministic automaton, it's impossible. So I'm asking, why can't you determinize the input?
We can talk it later. Thank you. No.
The third biggest setup, the machine is a continual drop. You will be presenting work that the university of Toronto with the article with neural interfaces.
Okay. Hello, hello. It's a pleasure to be here today. My name is Eugene. I'll be introducing Marple, which is a scalable spike sorter in hardware for portable brain-computer interfaces. I'd like to start off by talking about brain-computer interfaces, or BCIs, with some examples. So there's been a lot of recent advances in the recording, implantation, and processing technologies that have really pushed the envelope for what we see as possible. This community in particular has made several key innovations in BCIs just in the past few years. And there's been a growing interest in press coverage and industry investments that's very much propelling this forward. Just a few months ago, we saw a very high profile but controversial case of Neuralink, where a paralyzed man played online chess using just his thoughts. So BCI is a portable closed loop system where the thoughts of a user are automatically interpreted to aid and affect some sort of change. For example, that might be controlling a prosthetic limb or to mitigate an epileptic seizure. In this portable closed loop system, the environment is highly constrained, especially for day-to-day use. A BCI has to be fast enough to react to the millisecond timings of the brain, has to be low power enough to avoid brain damage from thermal discharge and cell death. It has to be small enough to be implanted without encumbering the user, and all while scaling up in order to improve the accuracy of neural decoding. Now, in the case of Marple, we're able to achieve this at 7 nanometers by operating at 300 megahertz, running at 79 milliwatts, 4.3 millimeters squared, scaling up to 10,000 channels. A lot of BCIs employ a technique known as spike sorting, and that's a signal separation process that determines if, when, and which particular neuron has fired. Spike sorting begins with inserting a neural probe into the brain to record signals from neurons. A neuron communicates by firing, which is producing a voltage difference called a spike. And spikes are unique to each neuron. Neural probes receive these spikes on the electrodes or channels, and often multiple probes are used simultaneously. Now, spike sorting is made difficult by the noisy environment of a brain and the problem of superposition. To demonstrate this, let's say this red neuron communicates to another one, and we pick this up on this purple channel and its neighbors. We actually see voltage variations in the circle of channels where the spike shows up, and this is actually very helpful because it gives you spatial and temporal data points. The problem is if another neuron, say this green one, fires at a similar time and in close proximity, it ends up contaminating the red one's signal. So often we'd like to identify both of these neurons, but now both signals are contaminated and superimposed. And as you can imagine, this problem gets much harder with the more neurons that you can simultaneously record. Now, to actually process these voltage recordings, a spike sorter performs multiple steps. The first thing to do is to clean up the signal, where a bandpass filter and spatial whitening are used. What this does is it removes noise from the background hums of the brain, other artifacts, and signals that are too far to appropriately detect. After taking this clean signal, the next step is to detect for spikes. So detection is generally based on a threshold. If a signal is strong enough, we just classify it as a spike. The spike is then aligned, which means a window in time is selected around it so that it can be further processed. The final step is to match the spike to templates, which are pre-recorded signatures of neurons. To identify which neuron the signal comes from, I'll clear this up. So a template is like a fingerprint of a neuron. And just like a fingerprint, each neuron has a unique template. Template matching, as the name implies, is this process of finding which neuron the incoming spike is actually from, or whose fingerprint this belongs to. This is calculated very simply using a dot product between the templates on a given channel and the incoming signal. So in the example on the right, we can very easily see that the blue incoming spike matches much more closely with the orange template than the green. Now, along with the problems of a noisy biological environment and superposition, one of the key difficulties today of spike sorting is scaling up. If you attended Professor Bhattacharjy's keynote from last year's ASPLOS, you might have seen this figure, but essentially it says that every few years, there's a doubling of the number of simultaneously recorded neurons. This is sometimes been referred to as Stevenson's law or Moore's law of neuroscience. Now, the growth in data causes an equal growth essentially in the compute and memory demands. And so with this doubling, it's actually accelerated just in the past few years. The original study measured in 2011 that there was a doubling of about 6 to 7 years, but just in the past, from 2017 and beyond, we see the doubling has sped up to just about 2 years. Now, with all these difficulties, modern spike sorters today have two main deficiencies. The first one is that if they operate online, they only do so on small numbers of channels using a limited subset of what's available. The inverse is that if they operate online, they can only, if they operate on large scales, they can only do so offline. And so they can't be used in a reactive closed loop system. For Marple, we have three main contributions. The first is that we develop an analytical model to find where the bottlenecks are for scaling up in spike sorting. Second is that we design a hardware accelerator that scales up to 10,000 channels. It does so in an online fashion, a power efficient and small form factor. And using the analytical model, we develop a compression pipeline that reduces the overall memory by about 5.7 times. And the final thing is we implement a highly accurate neural network that's an alternative to template matching, which reaches up to about 92% accuracy on our 10,000 channel benchmark. So the first thing is we built an analytical model to identify the compute and memory requirements of the various stages in a modern spike sorter. This helped us identify that for the scale of 10,000 channels, the templates for matching take up to 90% of the overall memory requirements, and that becomes the major power and area bottleneck. To counter this, we basically developed a compression pipeline that reduces the template memory. There's a lot of steps to it, but you can find those details in the paper. I'd like to talk more about the key observations that we took advantage of. And the first is that there's a relative dynamic range of templates, and it's quite limited. And that allows you to use more efficient data formats right off the bat. The second is that template shapes are quite similar between different templates. And so we're able to use clustering to find groups that share similarities and extrapolate. And finally, we exploit the fact that a spike's biophysics are quite predictable. An analogy for this would be to say, if fingerprints are all unique, they all still belong to fingers. So applying our compression pipeline on a small and large data set, we're able to reduce the template memory by about 8.1 and 11.3 times respectively. And this shows good scalability in the approach since the larger data set actually has a greater compression ratio. The compression is performed offline when templates are calibrated and generated, and we use a fast decompression engine for the online. Now, one of the primary goals in designing Marple's hardware is for scalability at a low power and area footprint. So to achieve this, we chose very simple compute units that operate on the data serially, and that matches the format that the neural probes actually record in. So each channel in space arrives one after another for a single unit of time, and then are processed as such. Marple has a front end and a back end, where the front end is composed of the noise removal, detection, and alignment steps that we saw before, and then a back end, which by default would be template matching, but we also evaluate it with the alternative of using the neural network-based approach. To evaluate Marple, a configuration of about 10,000 channels was implemented in a 65 nanometer process. So both the area and power are dominated by two stages, sample buffering and template matching. And those stages together account for about 95% of the total area and 84% of power. So at 65 nanometers, Marple takes about 109 millimeters squared and uses 1.4 watts, which greatly exceeds the budgets I showed before. But if you scale down Marple from 65 to 7 nanometers, that reduces the power and area footprint to within an acceptable range. Our final contribution is implementing 3 sizes of convolutional neural networks, CNNs, as an alternative to template matching. So instead of matching to an individual neuron with template matching, we just let the CNN figure it out. The CNN actually performs very well with an accuracy range of about 85 to 92% on 10,000 channels, and that's against 67% of template matching. However, practically deploying this alternative is very difficult since the memory demands of even the small model exceed template matching by about an order of magnitude. To conclude, Marple's contributions are a first stab at identifying and implementing real-time solutions to the growing scales of recorded neurons. We built a hardware accelerator for spike sorting that can operate in real time for up to 10,000 channels and demonstrate that there's great potential in using neural networks in spike sorting. With all that said, thank you.
Is the template matching kind of like word information?
No, it's literally just a dot product, I guess. I don't know if you might be able to use some kind of Fourier transform there. I'm not super familiar with Fourier transforms in hardware, so yeah.
Hey, Mohammed from Yale. So I was curious about the CNN. So what is the inputs to the CNN here?
Yeah, the inputs are the exact same as you would get from template matching, and that's just the waveform across several channels. So you have the center channel as well as its neighborhood.
I see. So how many samples would that be?
That's usually 60 by 9. So 60 samples in time, 9 by space.
I see. Yeah. Okay. And I see. Okay. Yeah. Thank you.
You kind of formulate it as like a CNN, a classic CNN matching picture problem, right?
Gotcha. Yeah. Okay. Thank you.
My name is Kevin from the University of California. Thank you for your talk. I'm very curious about how you're implementing your hardware accelerator. Is it like in RTL or HLS, and what kind of technology are you targeting?
Yeah, we used RTL. One of my co-authors, Amir Abdelhadi, he was kind of the lead on it, where I did more of the software side. I can definitely reach out to you and send you his contact info to talk more.
Thank you.
I'm sorry I can't answer more, but. Yeah, on average, you can say there's roughly 3 neurons per channel. That varies from all the way down to 1. So literally just 1 neuron is detected up to about 11 in our data set.
So the next speaker is this one. So he would like to be doing for the schools too. So we have to do all the work. Saha, who's currently at Neighbour, and Maya Nami, who's finishing PhD this year. And Maya is currently in the job market, so probably wants to follow up on the talk.
Great. Thank you. It's a pleasure to be here to talk about the work that my students did. It's too bad that they're not here to do it themselves. So what I'm going to talk about is an accelerator that we built for making RTL simulation run faster. And I'll explain to you why it's important and what we did. So those of you who design hardware know about RTL simulation. That's the way you describe the function of the hardware, typically in a hardware design language like Verilog. And then you run it on a simulator to see whether it works, to do testing, to do verification, to do debugging. The problem is that the simulation is slow. It can take a week to simulate an hour of execution time if you're using a high-speed processor. And this poor performance becomes a bottleneck in your design process. It takes a long time to find the bugs, takes a long time to validate. And we're building more and more accelerators. We have sessions on accelerators, and they're using larger and larger chips, so they're taking longer time to simulate. So how do we make simulation run faster? Well, it used to be you ran it on a bigger machine, but the machines aren't really getting that much faster, so the obvious answer is use parallelism. And it turns out that there's a tremendous amount of parallelism in RTL simulation. Hardware has a lot of parallelism, and so we should be able to take advantage of it. And the question in this, underlying all of this, is can we take advantage of RTL's parallelism to make the simulation run faster on hundreds of cores? So a little background first. What's RTL? It stands for Register Transfer Level Description of Hardware. And so what you think of is the hardware consists of registers which hold values. They're clocked. And so when the clock goes off, the edge goes up, you read the value on the input signals and you store it in the register.
And then there's logic between the registers, which basically computes new functions of the inputs. And this is the way you describe much hardware, much of the hardware, not all of it, but most digital circuits for sure. And so you have descriptions, net lists like that, which the square blocks outlined in red are registers, and the blue is the logic that computes new values. And so we start from this. And what we want to do is cycle accurate simulation. So we're not trying to do timing simulation. We're not trying to do power simulation. We're trying to see the functionality of the circuit. And so you start from a circuit like this. And what you do is you split the registers into two. There's a current value and the next value. The current value is what you're computing with, the logic is computing with, and it's producing the next value. And then when the clock goes off, the next value becomes the current value for the next clock cycle. So, it's called double buffering in other areas, but the hardware people, they call it current and next. The other way to look at it is that you can turn this into a DAG, where the registers are input at the top, and the round circles are the logic that they're computing, and then the registers that you're computing for the next step are at the output at the bottom. And the way in which simulation is typically done, even though not all the people label it this way, is with an idea called BSP, bulk synchronous parallel simulation. It's an idea that was introduced by Leslie Lamport about 30 years ago. There's two phases. There's a compute phase and there's a communication phase. In the compute phase, each processor computes its part independent of all the other processors. So if we have the net list there, we can color them by processor, and you can see the first processor P1 computes L1 and L2, L3 runs on processor P2, and so forth. They all compute independently. They use their local values. And then we come to the end of the phase and we synchronize so that we can do the communication at the same time as the clock cycle would have gone off. And so there's a barrier there. And then we do the communication phase, which then sends the values from the producers to the consumers. And we do another synchronization to basically make sure all the values have arrived before we start the next step in the computation, or the next clock cycle if you're thinking about it in hardware. So what are the limitations on simulation speed? Well, we can write out a fairly simple model, which is going to tell us that the x86 is not going to work very well for us. And so the simulation rate is on the left-hand side there. So it's the number of cycles we can simulate per second. And N is the number of cores. F is the frequency of the processor we're running on. There's the work per core, and there's the cost of the barrier. And we have the communication cost in there, but we're just going to ignore it for now and assume that it's close to zero. So the problem we're going to have is the cost of the barrier. We're assuming that the cost of the barrier is linear in the number of cores. You could make it logarithmic, and it doesn't really change the analysis either. So you compute the derivative, and you basically get this point at which the performance is maximum. We call it N collapse, and it's proportional to the square root of the work divided by the cost of the barrier. And this is the crucial ratio. The cost of the work is W is very low. The amount of computation it takes to simulate the logic is a very small number of instructions, maybe tens of cycles. The cost of a barrier on a large machine is very high. It's thousands of cycles. And so this disparity is where we get the curve that goes up, and then it plateaus pretty soon there, and then it falls off. So what do we do? Well, the answer is we basically want, I'm sorry. I forgot to say that we have an experimental demonstration in the paper if you want to see more. To tame the synchronization cost, what we're going to do is we're going to make the barrier constant time. We're basically going to get rid of this proportionality factor. And the way we're going to do that is by designing our own architecture that makes it possible. And then you can get a curve that goes up as the parallelism increases, at least until you run out of parallelism in the program. So the solution we have is an architecture which we call Manticore, which is a hardware-software co-design. We designed the architecture, we designed the compiler, and we implemented it on an FPGA, and it actually runs on the FPGA. So the key idea is we have a high cost for runtime synchronization. It limits our scaling to, tens of cores is pretty optimistic, probably less than that. We want to go to hundreds or thousands of cores. So we want to get rid of the cost of synchronization. So what we did is we built an accelerator, literally an FPGA that plugs into your workstation that does this acceleration. And it consists of a network of cores, which are custom cores, very simple cores that are connected by an on-chip network, which is a torus. And the whole thing is lockstep execution. There's a single clock for all the cores and all of the network switches. However, it's not single instruction. Each one of the processors has their own instruction. So it's multiple instruction stream, not SIMD like GPUs. We use local memories so that we can access them in constant time, and we have predicated execution, not branches. And the consequence is that we can predict at compile time exactly when things are going to occur. And so we can do scheduling at compile time. Those of you who know about the MIT raw machine, this is very similar to the idea. They tried it for general purpose computation. Didn't work well because the programs were dynamic. However, RTL programs are extremely static. We can analyze them very well in the compiler, and we can schedule them at compile time. So there's a little bit that's non-deterministic. If we access DRAM, the time it takes to access DRAM is non-deterministic. If we interface with the user at the console, that takes non-deterministic time. We play a trick by basically turning off the clock to the processor network there and making it appear as if it was a synchronous reference. Some more details in the paper. So how does it work? So we have two cores here, each one of which has its own instruction stream. Notice they're running different instruction streams, but they're going at the same rate. They're basically lockstep execution by PC, but different code. And then we're doing message passing, explicit message passing across the torus, and we're scheduling it at compile time. We're overlapping the computation and the communication, so we're reducing the communication there, and we're scheduling the network traffic so we have no buffering in the network at all to make the network very simple and very fast. What we do to eliminate the barrier is we basically introduce a delay at the end of this slower core, which in this case would be 1. We basically introduce a bunch of no-ops that cause it to wait for the core 0 to finish computation. The same effect as a barrier, but really no runtime cost because it was introduced by the compiler. Again, see the details, see the paper for the details on the compiler. So how does this work? Well, it works very well. So the compiler is crucial to this. It parallelizes the network net list. It partitions it among the cores. It schedules the instructions to make sure that they execute at the right time. And it schedules the messages. And it's only possible because hardware description languages are both static and easy to analyze. And it's not surprising. You don't have pointers in hardware. You don't dynamically allocate hardware. The net result is that the hardware we designed is very simple and very fast. So we're able to put 225 cores on a medium-sized FPGA that costs a few $1,000s, then plug in your machine, and it runs at 475 megahertz, which is pretty good for that FPGA. Again, see the paper for details. So, evaluation. So we ran it on 3 platforms. The first one, the AMD, is a very high-end recent AMD server, 120 cores. The next one is my student's gaming machine, which we overclocked to get as fast as possible. And then the final one is Manticore itself. So you can see different numbers of cores, different frequencies, different amounts of memory. So you probably can't read this, but this is the simulation rate. So higher is better, faster on these. And Manticore is the bar at the right. And you can see that we win in all cases, except for the last one, JPEG, which I'll talk about in a second. In most cases, substantially. And what we're looking at is the performance improvement, and we don't see much performance improvement with Verilator running on the x86 processors. In most cases, the performance is regardless of how many cores you throw at it, is pretty much fixed. There are a few cases where it speeds up, running with up to 6 cores. That was the largest speed up we got on these benchmarks. If you run larger benchmarks, you can go up to about 10 cores or so and see some speed up improvements. And then there's JPEG, which we do terribly at. And the reason is that JPEG, at least the implementation we have, is very sequential. And our processor is running at 475 megahertz, and these are running at up to 10 times faster, the x86 processors. So, you know, if you're doing sequential code, raw clock speed matters. So, in conclusion, general purpose parallel computers are pretty poor fit for RTL simulation because it's very fine-grained parallelism, and that's not what the machines were designed for. Manticore is the architecture we designed for scalable RTL simulation. We can go up to hundreds of cores. We built the compiler and an FPGA simulator, FPGA accelerator of it, and it runs, you know, FPGA simulations. Key takeaways: if you have a deterministic machine, you can statically schedule BSP, and you can get rid of the runtime overhead that way. And simple hardware that you get from this, where the compiler does all the complexity, means that it runs very fast and you can put lots of cores and get lots of parallelism on a small die. All of the code and the details of the FPGA are available online. Thank you very much.
Okay, so I'm going to, John Deming, Microsoft. Yeah. I'm going to ask the obvious question, which is, how does this compare to prototyping FPGAs?
You mean by actually taking the Verilog and producing? Well, the turnaround is much faster. So our compiler can take a design and compile it down to Manticore in a matter of minutes, worst case. And so you can have a much faster turnaround loop. So instead of waiting maybe a day for your large design to be compiled down to the FPGA. Also, simulation has the advantage that you get more insight into the FPGA and you can, you know, debug it easier, which is why people use Verilator in addition to the faster turnaround. So
how do you implement the visibility into this?
Well, you have the front end, and you basically communicate with the Manticore, and we play that clocking trick so that we stop the computation while the communication is going on. So it appears synchronous.
Thank you.
So you can see the state.
Thank you.
Joseph Torrells from Illinois. So this is very fascinating. Have you thought about other problem domains where you could apply this?
Such as?
AI, maybe, or some
AI. Nah, why would anybody want to do AI?
Learning, no?
You know, it's actually kind of funny. So this was submitted to last year's ASPLOS, and the follow-on work, which is under submission right now, is we actually used an AI machine to do this whole thing. We used the GraphCore machine, which has a tremendous amount of parallelism in it, up to 6,000 way parallelism. And we actually can run very well on that machine. So I think the answer is yes. There is a very close connection between this type of simulation and what you want to do for AI, because they're both very fine-grained computation.
And compiler analyzable, maybe.
I think it's harder to do the compiler analysis for AI than it is for RTL. But I don't think it's, you know, I think that the numeric cores are fairly not very dynamic. And so it is possible there as well. Yeah, that's the equivalent of a barrier, is that you basically have to finish the compute phase at the same time on all of the cores. So if you put them all, if you take all of the work and put it on the same on their own core, then the straggler determines how long it takes for that step. And so, you know, what happens is that we end up having more work than we have cores. And so we end up scheduling multiple pieces of work on a core. And so we try to even out the amount of work on a core so that they all finish at roughly the same time, so that there isn't a wasted no-ops time. And that's actually a hard problem because it's, you know, one of these NP complete problems that doesn't have a clear solution.
Okay, very good work. Jibin from Chinese Academy of Science. So I noticed that you consider the barrier synchronization. Do you consider other kinds of synchronizations?
We didn't. If you look at other work, in particular, the simulator that most people use, Verilator, uses a variety of different types of synchronization. So yes, but you know, the problem is that all of these other synchronizations on a conventional machine, on an x64 machine, are expensive. The cost of doing a lock, acquire, release, even a user space lock is hundreds of cycles. And if you're computing tens of cycles and then it costs you hundreds of cycles to synchronize, you quickly sort of run out of parallelism.
Okay, so do you show in the paper, do you show the scalability of the Manticore simulator? So I just now see you can extend
there are a lot of numbers in the paper. And
okay. Okay.
So
thank you.
Okay, sir. Thank you.
We have a time clock. Speaker forgot to send me the bio, so I'm guessing
Oh, okay. All right. Hello everyone. I'm Zihan from Georgia Tech. I'm advised by Professor Tushar Krishna and Arrvindh Rochester. And it's my great pleasure to present our work, Arrvindh, accelerator generation framework for optimization-based robotic applications. And the leading author, Yuhao and Yiming, they are not able to travel here, so I'm here to on behalf of our team to present. This is the outline of my presentations. So we'll start from the background and motivation. So we know that autonomous like a robot, they have achieved a wide range of applications, and they usually rely on some like different optimization-based algorithms, such as the localization, planning, and control. And these three core like optimization-based algorithms, they can work together. For example, the planning algorithm, they can generate a reference trajectory, and the localization algorithm, they can estimate the robot states. And also the control algorithm, they can calculate the system inputs and outputs. And each of these three algorithms, they can be formulated as a nonlinear optimization problem. And that is solved by a set of the optimal solutions X by minimizing the object functions fx. So this is the solving procedure of these nonlinear optimizations. So we start from this initial value, and then we'll construct and solve a linear equation systems. And then we will update this initial value with the solution, and then determine whether it's converged. If it's converged, then we'll obtain the optimal solutions. And if not, we'll rerun this this loop. And the core of this solving this nonlinear optimization is to construct and solve a linear equation like systems with the coefficient matrix A and the vector B, and also do the matrix decomposition. However, in most of these robotic applications, so the matrix equation is pretty large, such as in this is an example in the localization. We have the thousands of the rows by the hundreds of the columns in these problems. And this results in the very high latency, compute latency and energy.
that constrain the efficiency of the practical applications of the robot. Therefore, the architecture community has proposed several solutions to design the accelerators for this robotic computing. So the first type of solution is these programmable accelerators, which is great to accelerate different algorithms, but it may, like limited the performance improvement because they are like sometimes they're not able to leverage the unique features of the algorithms. So here that in the table on the right is the example of the robot applications where all these three algorithms, they need to solve matrix equations of the hundreds of dimensions. It's their sparsity level is around 95%. And the other direction of the solution is to design these dedicated accelerators, which is kind of achieve high performance, but sometimes they cannot generalized because of this significant difference between the different robotic algorithms. And also if we stack the different accelerators for each stage, it will also incur a large error and silicon overhead. In addition, different robotic applications, they also may require the different algorithms. For example, in a simpler manipulator problems, so probably only two algorithms, the planning and control, are needed. However, in complex this drone navigation, the three algorithms are needed. So a single accelerator is not suitable for these different robotic applications. So in this work, we hope to generate the accelerators for different robotic applications by mapping a different algorithms onto intermediate representations. And these representations need to have the two features. First, it can represent different robotic algorithms, and also it can utilize some sparse structure in the algorithm. And our insight of this work is we can actually leverage the factor graph, which can serve as a unified intermediate representation. And here we design first we design a software library to realize the transformation of the different algorithms to the intermediate representation, and also a compiler to realize the mapping of this different representation to the hardware accelerators. So what is a factor graph? So factor graph is essentially a graph model that contains two kinds of nodes. So one is the variable node that can represent the robot state, and also the factor node, which is represent a measurement or constraint. And also we have the edge to represent the dependence of different factors. So say the example on the right is the localization problem on the robot. So we have this so we have a camera and MU in this example, and have the X1, X2, and X3 as a pose, and also to observe the two landmarks, where is on the top, the Y1 and Y2. And we have both camera observations from F1 to F3, and also the MU observations from this F4 to F5, which this different variable node and factor node from this factor graph. So in these localization problems, linear equations you can see here, we need to solve with that with sparse sparse structures. So each factor node in this factor graph can represent a block row of the matrix, and each factor, which is a small black dot, represents an element in this solution vector. So in that case, the factor graph can represent linear equations systems and can be solved in these robotic applications. And next, let's take a quick overview of this Arrvindh framework. So we propose this Arrvindh framework as an accelerator generation framework, which first we have this software stack, which we use the factor graph as unified abstractions and build a software library for that. And then we have this compiler stack, which we transform this a bunch of robotic algorithms into this unified factor graph representations. And then we also have this accelerator stack, which we built an accelerator so the different algorithms can run together on this accelerator. And through that, we can improve the performance, scalabilities, and hardware resource utilizations of the application. And let's take a look of each stack. So the first is a software stack. So this through this software stack, users can implement different robotic algorithms to build their applications using the factor graph software library. So why we need these unified pose representations? So you can see like many different pose representation exist in the field of robotics, and they can be transformed into each other. However, like this diversity can create some problems. So the first problem or the first challenge is to, this diversity make it hard to build software and compiler to translate different algorithms into a consistent set of the instructions. And the second challenge is efficiency, because when the robotic community they design these algorithms, so they mostly design for the mathematical purpose instead of for the computational efficiency. For example, here this is a pose estimate pose representations. So you can see here we pad many zeros and ones into this matrix, which is not useful computations and also introduce many overhead during the real-time deployment. So for these reasons, we propose unified pose representations, and it contains only useful information about the pose. And here we summarize all these computations associated with such a pose, and defining a generalized addition and subtraction here. So addition can represent a transformation in the pose, and subtraction represent a difference in the pose. And based on that, we refine this robot operators in a generalized addition and subtraction. So here, it includes the rotation, matrix multiplications, transpose, and some of the rotation matrix vector multiplications, etc. And we only need these robot operators and derive the differentiations of these operators, and then we can get any values of any composite operations and construct the linear equations system for the different robotic algorithms. And based on these unified pose representations, we define these vector graph software libraries. So essentially, users can pick vectors from this library to build their own robotic algorithms. And so in that way, users can represent their algorithms by constructing a vector graph. So here is the same example we just saw before of these localizations. So we can add this cameras, observations, MU observations, and to construct a vector graph to represent these problems. And vector graph is essentially very efficient to solve these nonlinear equations. And next is the Arrvindh compiler stack. So the Arrvindh compiler can translate the high-level user code into both vector graphs and also this data flow graph of this matrix operations. So the node of this vector graph donates the robot operators. So the forward computation donates the computation of the values, and also the backward computation is the computation of the differentials. And also each vector node in this vector graph corresponds to a data flow graph of this matrix operation. And this compiler performs the forward traversal and also the back propagation of all these data flow graphs to construct this vector and a matrix in this linear equation systems, which we just discussed. And also these linear equation systems can then be solved by performing the vector graph inference, including the variable elimination and the back substitution. And then we have this accelerator or hardware stack, which we can generate accelerators from the user constraint compiler generated instructions, and also our predefined hardware template. So here is the example. Say the users can indicate a resource constraint. The optimization solvers here can solve for the number of the replicated computation unit for this matrix operations, such as the latency. Say we're trying to minimize the latency while trying to satisfy the resource constraint of this robot. And this is the overall architecture of our generated accelerators. So the vector computing module on the left is responsible for the forward transversal and back propagation to construct the linear equation systems. And the vector graph inference on the right is to solve the linear equations, and also the instructions can be executed on the out of order way in this accelerator. So and this accelerator supports the 3 level of the out of order execution. So the first level is the fine-grained out of order execution inside one algorithm. And the second level is the coarse-grained out of order execution between the different algorithms. And third is the out of orders in the like factor graph inference of the procedure. And for more details, please refer to the paper. And finally, let's see some result. So we evaluate this accelerator in the 4 robotic applications and with the 3 different type of the algorithms which have a different variable dimensions. Yeah, and we implement the accelerator on the Xilinx FPGA board and compare with the design with the different baselines, including the general purpose CPU and GPU, and also the accelerators. So here for the accelerators, the first accelerator is we directly accelerate these matrix operations without considering any pose or any sparse any sparse structures where we call it vanilla hallucinations. And also the second accelerator is we design accelerators for each a task and stack them together, which is we call it a stack here. And we provide 2 variations of the RNN. One is the in-order execution, and the other is out-of-order execution. So we first show the accuracy comparison, and we can show we can say the RNN can achieve the same accuracy compared to the software library implementation. And we also and then we compare the RNN with the 3 processors. So the first is like this performance. You can see the x-axis is the different robotic types, and y-axis is the speed up. And we observe the RNN accelerator demonstrate like a speed up compared to the general purpose CPU and GPU. And then we compare the our design with these 2 accelerators, and we see that we still achieve this speed up and with this vanilla design, and also the comparable speed up with we design the separate accelerator for each task and stack them together. But here we only have the one unified accelerator that can run a different algorithm. And finally, we perform a comparison with the accelerators in terms of the resource utilizations, where the x-axis is the different type of resources, and the y-axis is the our improvement. And we can see that we reduce the resource consumption compared to the baseline. So finally, the conclusion, and in this work, we propose this ARANA is an accelerator generation framework for robotic applications with for these multiple optimization-based algorithms. And we have this ARANA software stack where we use the factor graph library as a unified representations. And we have this compiler which can translate a bunch of different algorithms into a unified vector graph representation. And then we have these accelerators which can run a different robotic algorithms. So with that, I will conclude my talk. Thank you for the time, and I'm happy to answer any questions.
Hi, thank you. Good talk. So I have a question on the power constraint, because you said drone or swarms are one of your applications, right? So do you apply the power constraints on your generator of hardware?
Yeah, so the power constraint, I would say this power constraint comes from 2 fields. One is the robot field, say if you have a drones and if it's battery support, then the battery itself will have the power constraint. And second is a hardware constraint. So if we want to build a hardware within this 1 volt or like that. Yeah, so we consider this power constraint and add this analytical optimization problems, so we can solve these problems to determine how many compute units we can have under this power constraint.
Okay, thank you.
Thank you.
That I think you want to hear about.
Yeah, thank you.
name's Yang.